Hi, in this video we're going to be talking about transformations and piecewise functions. There are three different types of transformations that can happen. There are the flips, which are these first two. There are slides that happen in these middle four, and then these last four are stretches and shrinks that can happen for our function. Now, all of these vary a little bit based on whether that transformation is outside of the function or inside of that function. So let's take a look at a few examples. Here we have a series of square root graphs. The first one is being shifted down one. Up and down is outside of our function and it goes the way we think. And so we want a -1 outside of our function so that we can go down. Notice the -1 is outside of the square root. The second one is being shifted to the left. Left and right happens inside of our function, but it goes the opposite way that we would think. That left one, rather than being a subtraction, is actually a plus, but we can see that inside of our function. The last one has two transformations. We're moving to the left, three and up 1. The left 3 is going to be inside of our function as an addition, and the up 1 is going to be outside of that function also as an addition. Left and right happen inside of our function, and up and down happen outside of our function. Now we can use that table in order to identify what the domain and range of each one of these are. The first one is being down 1. That is a shift in our domain. So normally it would be 0 to infinity for both, but because we have that -1, we're going to -1 from that domain. 0 minus 1 gets us -1, and infinity minus 1, well, that's just still infinity, so it does not change. With our left one, that is going to be a change in the domain of the function. So we're going to change that x value. We're going to add 1, well, subtract 1 from our x value because we moved to the left one. 0 minus 1 is -1. Again, it's backwards from what we think when we're inside of that function. But the range doesn't change. And also, again, infinity minus 1, still infinity. The last one has a change in both the domain and the range. The domain is being shifted left 3, so we're going to subtract 3 from 0. And the range is being shifted up 1, so we're going to add 1 to 0. 0 minus 3 is -3. 1 plus 0 is 0. And both of these infinities, when being subtracted 3 or added 1, do not change because it's infinity. It's already huge. In these examples, we have a series of square root graphs. This first one is being moved to the right one and then up 3. Right is inside of our function because left and right is inside. Up 3 is outside of our function. So the right one, we would think, would be a +1, but it's actually a minus. And the up 3 is outside of our square root, and it's going to be the +3. So outside is the way that we would make what makes sense. So when we see this one that's being moved to the right 3, I know that is going to be inside of our function, and it goes backwards from what we would think. Normally, I would think that a plus would be to the right, but it's actually a minus on the inside. It's backwards on the inside. But inside is always left and right. This last one is being moved to the left 3 and down 1. Left 3 and down 1. Left is inside of our function. It's going to be addition. And down is outside of our function. Up and down is always outside of our function, and it goes the way we would think. Talking about the domain and range of these graphs, right is a change to our domain. So we're going to add 1. Goes backwards from what we see here, but the range follows what we would think. So +3, we would add 3 to those zeros. Normally it would be 0 to infinity, 0 to infinity, but 0 plus 1 is 1. 0 plus 3 is 3. But the infinities, if you add 1 or add 3 to it, doesn't change it. It's infinity plus 1, infinity plus 3. It's still infinity. If we check this one, there's a change in our domain because we've got that -3. So we would do the opposite of that because it's backwards and weird on the inside. So we would add 3 to that 0 to infinity that normally shows up for a square root graph. And our domain is 3 to infinity. Our range doesn't change because there's no transformation to the outside of that function. In terms of the domain and range for this last one, that left 3 is going to be -3 on our domain. So 0 minus 3 gets us -3. And this -1 on the outside goes the way that we would think. It's normal on the outside, backwards on the inside. We would do 0 minus 1 to get -1. But if we subtract 3 or subtract 1 from infinity, we still get infinity. In these examples, I want to write some equations based on these words that are written on the screen. So I know I've got 3 units up, and that's going to be outside of our function. Up and down is always outside of our function. Goes the way we'd think. Up is add. 2 units to the right is going to be inside of our function, but inside is going to be backwards and weird. So rather than going to the right, instead I'm going to subtract on the inside of our function. And our absolute value function, that's just like that x with the little bar things. So inside of that absolute value, we're going to subtract 2. And then outside of that absolute value, we're going to add 3. When we talk about the domain and range for this thing, the domain is not going to change because it's going to be negative infinity to infinity. Yes, this 2 units to the right should change it, but negative infinity plus 2 is still negative infinity, and infinity plus 2 is still infinity. We are going to see a change in our range, though, because the outside is going to add to our range. So that normally shows up for an absolute value graph is going to go, instead of 0 to infinity, it's going to go 3 to infinity, 0 plus 3. In this example, we've got a square root function, which 3 units right and 4 units down. 3 units to the right, that's going to be inside of our function. It's going to be subtraction. It goes the opposite way while we're inside of that fraction. Up and down, that's outside of our fraction, so that 4 units down is going to be outside, and it's going to be subtraction because when we are outside of our function, it follows the directions that we would think. Our square root is just that little hook symbol, so we need to do a -3 inside of that square root and a -4 outside of that square root. When we take a look at the domain and range of that thing, that domain is going to be doing the opposite. So the opposite of -3, backwards and weird on the inside, it would be 0 plus 3 is 3 to infinity. And our range gets subtracted by 4. It's normal on the outside. There's a -4 on the outside. It's going to subtract 4 from what our normal range of 0 to infinity would be. 0 minus 4 is -4. Infinity minus 4, it's still infinity. It doesn't change because it's just too big. A particularly interesting type of function that we can graph are piecewise functions, which can be graphed by hand, but they're very annoying to do so. So I'm going to show you how you can graph them on a Desmos calculator. In this example, we've got a piecewise function here, and it decides to be 3 different things along the way. We can see that we've got a constant function, so I know I should expect a straight line when x is less than or equal to -2, but it's not going to stay that way, so I should see a flat line. Then I've got a quadratic, and I know a quadratic function is going to be a U shape, but it should be flipped over. Normally it would look like this, but it should be flipped over like that. And then finally, we should just have a basic linear, so just a straight line going through it. So let's see how to graph that on Desmos. So I've pulled up my Desmos calculator. I'm going to type in that first part of the equation, y equals -1. There's that constant function, but I don't want this whole thing. I only want it when the x values are less than or equal to -2. I don't want any of these points over here. To eliminate that stuff, you put a little squiggle bracket, and then you type in x, and then less than, and then in order to make it less than or equal to, you just type in equal right after the less than, so you get a less than or equal to, and then you type in -2. And then you can see that it just does that little chunk. Now I want a filled in dot there at -2, -1. So I'm going to type that in there so I know that there's a filled in dot. Desmos doesn't show that filled in point. So it's nice to kind of put it there so you know where the end is. And is it an open circle or closed circle? And I know it's a filled in circle because I've got that equal to right here. Now let's do the next thing. I'm looking for a parabola that looks like that. So I should get -x to the power 2. Yeah, there we go. But I don't want all of that thing. I just want the portion that's between -2 and 3. Otherwise, this thing wouldn't be a function. So I add in a little squiggle bracket, and I go -2 just less than x, which is less than 3. I'm just copying right off of right here, typing that inside of those squiggle brackets. Now, both ends of these are going to need open circles because there's not equal to's on there. So one of them is at -2, -4. And then the other point is over here at 3, -9. Now, the default is a filled in circle. In order to make them open circles, you click on this little gear here, and then you can click on the dot, and then you can say, hey, I want that to be an open circle instead. You can also use these to change the colors. So like if I wanted them all green, so that the quadratic is green and this one's red, I could do that if I wanted to, but you don't really have to do that. Sometimes it's nice if they're all different colors. Next, we've got that x, so that's just going to be y equals x. Notice that here I put the y equals there, I didn't. If it's not showing up, just add the y equals. And we want the x to be greater than 3, so a little squiggle bracket, x greater than 3. There we go. So that's just that portion of the graph. But again, here I want to have an open circle because I don't have an equal to there. So I want to make sure that at 3, 3, I click on the gear, click on the dot. I want to make sure that that is an open circle. And there's my graph of my piecewise function. So I've pulled that graph into our slides so that it's a little easier to talk about. We want to find the domain range where it's increasing, decreasing, and constant. In terms of this thing's domain, I can see I've got outputs all the way here in the negatives. I'm a little worried at -2, but I've got a filled in and an open and a filled in, so I'm definitely okay. Here, though, at 1, 2, 3, I am in trouble because I've got 2 open circles, so there's no output for our function at 3, so we have to skip over 3. This is continuing towards positive infinity. I'm continuing to get outputs over there, and I'm continuing to get outputs towards negative infinity in terms of the x-axis. So our domain is everything except for 3. This thing is going to be increasing right here. We're not going to be including this -2 because we got an open circle there, and we're going to be increasing over there from 3 to infinity. But -2 to 0, we are going up, and we're going up over here. This is our area where we're decreasing from 0 to 3. Note that I'm talking about these in terms of my x values, and then we're constant for these x values of -2, -3, -4, -5. So that is where we are constant. In terms of our range, our lowest value that we get is down here at -9. We don't get an output of -10. So that is not part of our range. This range goes all the way up to 0. We have a gap in our range right here. I don't get an output of 1, I don't get an output of 2, and I don't get an output of 3. So there's a gap between 0 and 3. 0 is included because I've got a filled in dot here. 3 is not included because there's an open circle here. But then this is continuing up towards positive infinity for my range. In this example, I've got 2 linear functions. I've got that decreasing function of -x, and I've got that increasing function of 2/3. I know that because of the slopes of that 2/3 and -1. I'll have an average rate of change for those two of 2/3 and -1. And then we've also got a constant function from 2. That constant function only exists when x is greater than 5. But then I've got 2 linears that are happening between -3 and 0, and 1 between 0 and 5. Let's take a look at Desmos to see what this thing would look like on a graph. So I'm going to begin with my first one. So I've got y equals -x plus 4. And then I don't want that whole thing. I only want the values between -3 and 0. So I just want this little middle piece. So I put a little squiggle bracket, and I want -3 is less than x, which is less than or equal to. To get that equal to, you just press an equal after the less than. And there I've just got that chunk that's between -3 and 0. Now at -3, I want that to be an open circle because I just have a less than there. So at -3, that is 7. I want an open circle, but then right here, I want just a regular circle, like a filled in one. So 0, 4 will be filled in. In order to make this one open, I click on the little gear, I click on the dot, and then I click on the open circle. So gear dot open circle. Now I've got that open circle marked. Next, I need one. The next function is 2/3 x, so 2/3. Get out of the denominator x minus 1. So there's my whole line, but I don't want the whole line. I just want it from 0 to 5, so this chunk of the purple line. So I get a little squiggle bracket. 0 is less than x, which is less than or equal to. So I just press an equal to after the less than and a 5. And there we go. There is our nice graph going between there and there. Now see, it is outputting that, and I don't want to output that. I want to be close to 0, but not include 0. So in order to remember that, I'm going to say, hey, Desmos, at 0, -1, I want to make that an open circle. At 5, and this looks like, well, I don't really know what that one is going to be, so I'm going to call it 5, and then I'm just going to write what I need to do. It's like 2/3 times 5 minus 1. There we go. Now it's on my spot. So rather than actually figuring out what that is, Desmos can figure it out. Or since it is just an open circle or filled in circle, you could just not bother with the dots. This is just in case you want to get that dot there. Finally, we've got that constant of 2, so I need to type in y equals 2, but I don't want that whole thing. I only want the parts of it when x is greater than 5. So squiggle bracket, x greater than 5, close the squiggle bracket, and then at 2, 5, I want another open circle. So I'm going to type in 2, comma 5. I'm going to, probably 5, 2, not 2, 5. And then I'm going to click on my gear, and then I'm going to make that an open circle. So that would be my graph of this piecewise function. So let's take a look at that in Desmos now, in the slides now. So I want to talk about the domain of this thing first. I can see here at -3, we get close to that value, but we don't get any other output. So -3 is not part of our domain. Here at -2, we do get an output. So -2 is part of our domain. Here at -1, yep, that is part of our domain because I'm getting an output. Here at 0, yep, part of our domain. I got an output there, but not there. We continue along until we get the next jump, which is at 5. 5, we do have output. We've got one filled in up there, but nothing there. So we continue to 5. And then this line just kind of keeps going. So this is going to go to infinity. So our domain is -3 to infinity, but I put a parentheses around that -3 because I've got an open circle there. Then we check our increasing. We're increasing only on this middle pit between 0 and 5, so we can just grab that inequality because that's the only thing that's going to be increasing. This one's decreasing all the time, and hey, this one's going to be our constant. So hey, guess what? This is going to be our interval for decreasing from -3 to 0, and this is going to be our interval of constant because that's a constant function. When we check our range, we can see our lowest value is happening down here at -1. This is covering up for our y value of 1 and 2, but we kind of hit this break right here, that 2/3 times 5 minus 1. Future me figured out what that was. We don't get here anything here at 3, but we pick up again here at 4 as part of our range. And then we continue our way up past 5. 5 is an output, 6 is an output, but 7 isn't quite an output. So that is a restriction on our range. We never quite reach 8. So our range is from -1 to 7/3 and 4 to 7. In this example, we've got another linear of -3x plus 11, and x, that -3x should be decreasing the whole time, and that x should be increasing the whole time. And our absolute value is going to be just our regular absolute value, so it should look like a v. So let's go into Desmos and see what this will look like. So we start out with that -3x plus 11, and we want to set the interval for that thing so that is 2 is less than x, which is less than or equal to. So I type that less than, and then I just press the equal button, 4. And then at the beginning of that thing at 2 comma 5, I want a dot, and I need another dot at 4 comma -1. Okay, of those two dots, I want the 2 to be an open circle. So I'm going to make that open. And then the 4 is going to be a filled in circle, so I'm going to leave that filled in. Okay, great. Next, I've got absolute value. To get absolute value, it's right above my enter key. It's got a little slash on it. I have to hit shift to get that bar, and then an X. So there's our absolute value, but I don't want the whole thing. I just want from -3 to 1. Okay, -3 is less than x, which is less than or equal to. So I just type the less than and an equal to and a 1. So there is our absolute value graph. I got a couple points on the end there. So at -3, 3, I'm going to want that to be an open circle. And then at 1, 1, I want that one to stay filled in. So let's turn the black one to an open circle. Finally, we've got just regular old x, so y equals x. There we go. And it only exists when x is less than 3. So x is less than, well, negative 3. But I probably should do it as curly brackets after this thing. X is less than negative 3. Okay. And at the end of that thing, at negative 3, I want to put a open circle. I've got an open circle because it's going to be less than that point. So there is my graph of my piecewise function. Looking for the domain of this function inside of our slides, we can see negative 5 is part of our domain because we want everything that's less than negative 3. So all of this stuff is going to be part of our domain. But right here at negative 3, I don't know where to put it. It doesn't go in this part of our function, and it doesn't go in that part of our function. We got two open circles there, so we're going to have to skip over that negative 3. I can put all the values between negative 3 and 1 because I can put whatever I want into our regular absolute value function. But right here at 1, we kind of stop. If I look at the values between 1 and 2, I don't know where to put them. I don't put them in absolute value because it doesn't work in this inequality. And I wouldn't put it in this top one because it doesn't work in that inequality either. So I get a little bracket at the end there. And so then we continue on at this x value of 2 because that's our final interval that stops at 4. So that is our domain because that's where we're able to put values into the function and get something back out. We know where to put them for these three parts of our piecewise function. If we think about where we are increasing, I know I'm going to be increasing on all of this interval and part of the interval of our absolute value. So I want all of this x is less than negative 3. And I just want this 0 to 1 part of our absolute value function. These are supposed to be brackets. It's hiding under the decreasing. It's decreasing on our interval for this function, so from 2 to 4. So we want to make sure that that part is decreasing. This should be a bracket instead of a parentheses. Sorry about that. And then we're also decreasing on this part of our absolute value. I want to put a bracket here because I got a filled in circle. These are ending with filled in circles, so those should both be brackets. This function is never constant because it's never flat. It is always slanted in some way, shape, or form, so no constant. Our range for this function, we look at what sort of output values we get. We get down here in the negatives, so we go all the way up from the negatives up to this value right here, which is negative 1, 2, 3. But we don't include that value because we've got an open circle there. The next output that we get for our function is over here at negative 1. We never output negative 2, so negative 1 is the next part of our range for our function. And we're getting output values all the way up here to 4, but then that range stops here at 5. So we get a parentheses at 5 because we don't quite include 5 because it's got this open circle there at 5. So our range ends up being negative infinity to 3, negative 1 to 5. In this example, I've got a piecewise function that has a quadratic. That quadratic has been pushed down 1 and stretched vertically a little bit. Let's see how that looks. And then the square root graph has been shifted 2 up as well. And they've got two separate intervals that we want to check. So let's go to Desmos to see what that looks like. We'll start with our 2x to the power of 2 minus 1. So we can see that stretched a little bit vertically because without that 2, it kind of gets a little like stouter and fatter. So it's been pulled up and stretched vertically. Then we've got a x is less than 1. And we want to make sure that the end of that graph, so at 1, 1, we want to make sure that that is a open circle because I don't have an equal to there. So I will choose a open circle for that endpoint. Then we also have that square root graph. If we want that square root symbol, I just got to get down to the bottom of my screen somehow. To get that square root, you can show that keypad, and then here's our little square root button. So x, I want to get outside of the parentheses plus 2. I don't want to be inside of our parentheses because that's outside of it. Then we've got our equation of x needs to be greater than or equal to 1 because we just want part of that square root graph. At the end of this thing at 1, 3, I want to put a filled in circle because I've got a filled in circle there because of the equal to. Pulling this into our slides, we can see that we're going to have a domain of all real numbers. There's a gap in what's going on between these two functions, but in terms of our domain, we get all real numbers because all of these values get outputs. We get an output here at 1, and we get outputs all the way towards positive infinity. We avoid that restriction that normally we get on square roots because we're staying greater than or equal to 1. With our increasing, we can see we're increasing from 0 to infinity, and we really make an increase here as we jump from the quadratic into the square root. This thing is decreasing until it reaches the bottom of that concave up section, so negative infinity to 0. And then this thing is never constant because it's always curved somewhat. Square root kind of flattens out, but it is still roughly increasing and never becomes perfectly flat. The range of this function, we can see the lowest value happens down here at -1, and then we get outputs at -1/2, at 0, at +1/2, at 1. We don't get an output here, but we do get that output of 1 over here. So 1 is part of our range. 2 is part of our range because we've got that output over here. Once we get up to 3, we start getting 2 outputs again. So we're definitely covered in terms of our range, and this thing is continuing to go up. So that makes our range -1 to infinity. In this example, I want to figure out what the equation of a piecewise function is based on its graph. So right here, I can see I've got a quadratic that is being moved to the left 4 and up 1. I know that left is going to be inside of that function. So it's going to be a minus, it's opposite of what we think, and that +1 is going to be outside of our function because it's moving up. I've chosen this less than or equal to -3 because I just want the part of the quadratic that's less than -3. I don't want this chunk because at -3 it shifts to a constant that's at 2 from -3 to -2. So I just write a 2 from -3 to -2. I've chosen to put this as a less than and this as a less than or equal to. You could reverse those equal tos because there's a filled in dot right here. One of them has to be the filled in dot and one of them needs to be an open circle. It doesn't matter which one's which. You just got to pick one for them. They can't both be the -3. After that, we've got this linear decreasing function with a slope of, oh, that's wrong. So it should be -5/2 right there. But I think I've got it right in the equation. Yeah, I've got it right in the equation. So -5/2, it's going from -2 to 0. And then we've got an increasing function here with a slope of 2/3. I got that one right. So up 2 over 3 for our slope. And this purple one is for right here. It's only existing from -2 to 0. Again, I picked this one to be the equal tos. I could have swapped these around. There's a filled in dot at each one of these points. So you just want to pick which one is the filled in one versus the not filled in one when you don't have those clear open circles. For the domain of this function, it's going to be -infinity to infinity. These things were fighting over each other to make sure that we are covering all of the domain. We can put any x value into this thing and we get everything out nicely. None of these equations are going to cause us any trouble. We're increasing from -4 to -3 in this little tiny chunk of that parabola, as well as the big chunk of this linear. We're decreasing in the rest of the parabola from -infinity to 4. It's a little bit, but that arrow makes it that -infinity. And then we're also decreasing from -2 to 0. Again, looking at those x values to talk about increasing, decreasing, and constant. And then our 2 here is representing our kind of constant area. That started and ended with filled in circles, so I put a bracket on the -3 and the 2. In my range, the lowest value is -3, and then I get outputs up and up and up and up and up, and you might think that there's no output here at 3, but it does keep going, because remember, this arrow is going up, so it's continuing to reach that outputs of 3 and 4 and 5, that both of these things continue to go up. But neither of them is pointing down, so I never quite reach that y value of -4, so that's why the lowest value of my range is -3. In this example, we've got a piecewise function. We want to figure out its equation. We start with a quadratic that's been shifted to the left 2 and down 4. So in our equation, that left 2 is going to be inside of our function. It's going to be a addition, backwards from what we think. I almost got said wrong. And then a minus 4 because we want to go down 4. We only want that graph to exist between the x values of -4 and 0, so we put this thing on there. Both of those are filled in circles, so that tells me I definitely want to put brackets or equal tos on both of those less thans. Next, we've got a linear. It has a slope of 1/2 and its y-intercept as 2. So I can just write that in nice slope-intercept form. This one's existing from the values of x values of 0 to 4. 0 has an open circle at it, the x value of 0, to the x value of 4. We have a filled-in circle there. So we want to put an equal to on the 4. Finally, we have a constant down there at -3. So we just put a value of 3. It's got an open circle at the x value of 4, so I want to put a greater than on that 4. And so that would be the equation of our function. Looking at the domain of this thing, our only thing that's going to be constant is that inequality of -3. That's our constant chunk. The blue part is going to be increasing that whole time because it is a linear with a positive slope, so that's going to be increasing. We're also going to get some increasing from our quadratic because there's a positive part of it where it's increasing, but it also starts out with that decreasing from -4 to -2. So -4 to -2, but we have this big chunk of increasing right here from -2 to the x value of 4. Our domain, our lowest value is -4, and we get outputs all the way here from our quadratic. We get outputs from 0 to 4 from our linear, and we get outputs from 4 to infinity from our constant. So our domain is -4 to infinity. In terms of our range, though, the lowest we go is -4. We don't reach -infinity. That's our lowest y value. And then we get y values up to 0. So those are all of our outputs from -4 to 0. But then at 1, there is no output. So 1 is not an output of our function. It is not in the range of our function. But values from 2 to 4 from this linear piece are part of our ranges, our function's range, because we get outputs here at 2, kind of. That's why we put parentheses. We get an output at 3, and get an output at 4. So that's our range. That's it for our video on transformations and piecewise functions. A reminder that translations are opposite when they're inside of that function. So when you go to the left, it's addition, and when you go to the right, it's subtraction. But on the outside, it is normal. Up is plus, and down is minus. Piecewise functions are just graphs that change their minds over different intervals, and the best way to graph them is using Desmos and using those little curly brackets to represent the different intervals of the piecewise function. Thanks so much for watching. Bye-bye.